Hey guys, we're back again with circuits, but this time we're actually doing the fun part of circuits, which is analyzing them and finding currents, finding voltages, using resistors in series and parallel. It's going to be awesome. I'm really excited about it. It's one of my favorite parts of physics ever, so today's going to be a good day. Granted, any day you're in my class is a good day, but this is going to be one of the better ones. So before we actually do circuits, you got to know what all of the things in a circuit mean. So circuit diagrams are drawn as a logical schematic for the way a circuit is going to work. They don't actually look this way in real life. It's not like they plot out the wires in rectangles or whatever, because that would take up so much space. They're way more compact than that in real life, but that's just the way that we draw them. There's a few symbols that are going to be super important. There's like many other symbols, but these are going to be the ones that are important for today and for this unit. The first one is batteries. There's actually two different symbols for batteries. I like to draw this first one because it's simpler and faster to draw, but most of the time in printed diagrams you'll see this second one here that's just got more little, just more lines. Something to note about the batteries that hopefully you found out in the lab was that the long side of the battery is the positive one. You actually need to know that to figure out the way things are moving in a circuit. So the longer battery line is the positive end, the positive terminal. The shorter one is negative. Next up is resistors. I've drawn these before in lecture, so you probably already know what they look like. They're these squiggly lines. Usually mine don't look quite that nice. They're a little bit more scraggly. After resistors, we got capacitors down here. Capacitors are what looks like two parallel plates. Imagine that. They look similar to batteries, so at a glance, you just need to know that a capacitor is the ones with two equally long lines for the parallel plates that are of equal area. And last thing is switches. That is a pretty obvious one. In a lot of diagrams, these are not open circles, they're closed circles, but I feel like you're smart enough to know that there's still switches. Open switch means the circuit's not closed, it's open. Closed switch is just basically like a wire. When we're working with circuits in real life, like in a laboratory setting, to measure current and voltage in the circuit, current gets measured with an ammeter at one point, because you can imagine current flowing through somewhere. You can just like read it at one point. That makes sense. If it doesn't make sense, I don't know how else to explain it. When you're using an ammeter, you place it in series with your circuit. We'll see what that looks like in a second. For a voltmeter, that's used to measure voltage, a voltmeter has to be placed across 2 points because you're measuring a potential difference between two different places. So if you got a long wire, you have to put your two ends of your voltmeter, because voltmeters are going to have like two measuring devices, I guess. Two probes is what you actually call it. People make fun of me when I say the word probe for some reason. Anyways, the two probes would be placed at two different points, and you're measuring the potential difference across them. And if you're going to put this into a circuit, like a built-in voltmeter, it has to be placed in parallel. And we'll look at why that is when we actually talk about the series and the parallel. So here's an example of a series circuit. It is a low-res image that I pulled off of the Googles because I didn't want to make one. Anyways, a series circuit is one where the resistors are lined up one after another and there are no junctions. So what that means is that charge flows from the positive terminal, which is the long end, the positive terminal, and it goes straight through resistors one after the other. It doesn't come across any splits. So the electrons travel in one path all the way around. That is a series circuit. So you could think series is things that come one after another, like a series of episodes or a series of books, a TV series. Those are things that come one after another. That's what a series circuit does, is it takes those resistors and they come one after another. Now, a series circuit could look a little bit different, like the resistors could be on 3 different sides, but as long as the electricity is flowing through it in series, it is a series circuit. Now, in a series circuit, due to conservation of current, the current through each resistor will be the same. Current through each resistor is the same. And this makes sense because as charge is flowing, the same amount of electrons that go in have to come out. So if you've got a current of 1 amp going through this resistor, there's nowhere for that current to go but through the next resistor, so that's also 1 amp. Same thing through the last resistor all the way around. The current doesn't change. However, the drop in voltage across each resistor could be different according to how much potential energy that resistor takes away from the current. So current's going to stay the same. Voltage across may vary, which we're going to find out is the opposite for parallel circuits. Voltage across may vary. Now, when we're evaluating circuits, there's going to be something called equivalent resistance. Actually, I should probably make a slide about this, but too late. Equivalent resistance is basically if you took all of the resistors of the circuit and made them one giant resistor, what the total resistance of the circuit would be taken as a whole. And to find that in a series circuit, you add up all of the resistors. And this is a fancy equation that says that. This giant E means sum. I is just an index. It would go over all of the resistors. It says the sum of all of the resistors is the total resistance or the equivalent resistance of a series circuit. And we're going to look at that here with this example problem. This problem says calculate the current and voltage for each resistor below. Graph the potential through the circuit starting at the positive terminal of the battery. So, first step in solving a circuit is to find the equivalent resistance. Step 1, find equivalent resistance, which is R sub S. That means the resistance of the series circuit. In a series circuit, you simply add all of these things up. So RS equals the sum over I of RI, which equals R1 plus R2 plus R3. So that's 100 plus 300 plus 50 equals 450 measured in ohms. That is the equivalent resistance of the whole circuit. So now we're going to use Ohm's law, which is V equals IR, to determine the total current of the circuit. The voltage in the circuit is 9 volts, which is given by the battery. 9 volts equals the current times the resistance, which is 450 ohms. You find the current is 9 over 450, which is 1 divided by 50, which is 0.02. Get I equals 0.02, and that is amps A. So that is the current flowing through the whole thing. Now, step number 3 is going to be calculate. Sorry, I can't spell calculate. Let's erase that. Calculate. Okay, we're going to calculate the potential difference across and current through each resistor. That's for each resistor. So let's look at resistor number 1. Now, the things we know about resistor number 1 are we know its resistance is 100, but we also know the current, because the current through the whole circuit has to be the same due to conservation of current. Everywhere in the circuit, the current is 0.02 amps. So we know V equals IR. Current is 0.02. R is 100. So the voltage equals 2 volts. That's how much potential drops over that resistor. That is all of those electrons losing enough potential energy corresponding to a voltage of 2 volts. Now R2 has the same current because the current is the same everywhere in a series circuit. So you get V for voltage equals I, 0.02 times the resistance, which is 300. The potential difference drop across that one is going to be 6 volts. So they lose a lot more potential energy, all of the electrons lose a lot more potential energy over a 300 ohm resistor than a 100 ohm resistor, which makes sense. And then for the third resistor, you get voltage equals 0.02 times 50 for a voltage of 1. So they lose 1 volt, not of potential energy, but the potential energy corresponding to 1 volt over that last resistor. Now, a way to check yourself here is to see that the potential difference across all 3 of those resistors should be the potential difference across the circuit. And if you look, that is correct. You got 2 plus 6 plus 1 is 9 volts. So as the electrons go around the circuit, they lose all of their energy to get back to the battery so that they can be energized again. And to see that a little bit differently, we're going to graph the potential through the circuit starting at the positive terminal of the battery. I'm going to start a graph here. This is going to be, let me scoot that up a little bit. Down here, this is going to be at the positive terminal. And this is going to be the voltage over here. So at the positive terminal, it's got 9 volts of potential. Because the potential difference across the battery is 9, we're going to make the negative terminal our 0 point. Now, as it goes through the first little bit of wire, so we're going to have some wire here, it doesn't change potential because we're assuming an ideal wire. As we get to the 100 ohm resistor, we have a drop of 2 volts, and we assume that's linear. That's one of the assumptions we talked about. So we're going to go down 2 volts to 7. This is at the 100 ohm resistor. Then we got a little short section of wire. Then over R2, we're going to lose 6 volts all the way down to 1. And I'm making that a steep slope because we're going to assume it's the same length as the 100 ohm resistor. This is over the 300 ohm. Then it travels a short ways at 1 volt through that little section of wire and goes through R3, which is a loss of 1 volt. So I'm going to make that one shallower. It's the 50 ohm. And we're at 0 for the rest of the circuit till you get to the battery again, and it cycles back through to here. So it's like a roller coaster, starting at the top, falling its way to the bottom, and then being lifted up again by the battery. Parallel circuits, on the other hand, are a little bit more complex. And you can see I have stolen yet another low-res image. But the deal with parallel circuits is that their resistors are in parallel. So you can see geometrically these resistors are parallel to each other. Now this doesn't really happen like geometrically that way all of the time in life. That's not how they're actually constructed geometrically. But it means that the electrons or the electricity are going to be running through both branches or all of the branches at the same time. So if you've got electricity coming out of this positive terminal here, when it gets to this point right here, this one, it's got a choice. Not really, because physics and determinism and whatnot. But it's going to be split between the two branches here. So it's going to go both ways. And when electricity is traveling through two regions at the same time, the current gets split. That's called parallel. And it's actually going to be going through all three of these. That's called a parallel circuit. In a parallel circuit, the voltage across each resistor is going to be the same and current is going to be split. So previously in series, we said current's the same everywhere and potential difference varies. It's the opposite for parallel circuits, and here's why. All of the conductors that are like connected together, all of the conducting wire that's connected together that doesn't have a resistor across it, a place for the electrons to lose that energy, all of that that's connected has to be the same potential. So I'm going to draw the areas here of same potential. Right here, all the way over, all of these have not yet crossed a resistor. They have not lost potential energy. So all of their electrons have to be at the same potential. The same thing could be said of the other side. Right here, all of these things that are in blue. There's no resistor, and they're all connected with no resistor. So they all have to be the same potential. This potential, the blue one, is connected to the negative terminal, so that has to have a potential of 0. And all of the red is connected to the positive terminal with no resistors, so their voltage has to be 9 volts, or their potential has to be 9 volts according to the battery. So the potential difference from the red side to the blue side of each of these resistors has to be the red minus the blue, which is 9 volts. Every resistor here has a potential difference of 9 volts. But they all have varying resistances. So according to Ohm's law, the current's going to be different. And that's because as the electrons, or positive charge carriers that don't actually exist in materials, move around this circuit, they get split up, the current gets split up into different areas. So the current changes based on the resistance and the voltage. To analyze this kind of circuit, it's a little bit more complex. You have to find the equivalent resistance just like we did last time, but you do that by taking the inverse of the sum of the inverses, which is quite a mouthful. Basically, you take 1 over each resistance, add all those things up, and then take 1 over that to get your total resistance. So let's see how it works in the next slide. Here we've got that same thing, 3 resistors connected in parallel. To find the equivalent resistance or the total resistance, we're going to have to do 1 over each of these things. Yay for fractions. So resistor 1, or well, I should write out the whole thing. We do 1 over resistors in parallel, the total resistance parallel, equals the sum over I of 1 over Ri. Okay, so what that looks like is 1 over resistance parallel equals 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3, which is equal to 1 over 10 plus 1 over 2 plus 1 over 1 is 1. And these are all in kilo ohms. I'm just going to ignore the unit till later, which is fine. 1 over 10 plus 1/2 is 12 over 20, which is equal to 3/5 plus 1 is 8/5. So 1 over resistance parallel equals 8/5. I hope I did that math right real quick. And so to find the resistance parallel, you do this to the negative first, or you take the reciprocal, which says that the total resistance parallel equals 5/8, which is significantly diminished. I mean, look at these resistors. You got 10, 2, and 1, and your total resistance is 5/8. That's a weird consequence of the system that most people would not expect. And it's because as the electrons spread out, it's easier for them to get through things. It's like a greater area and less people trying to go through. It's like if you had 800 people all trying to get somewhere and you had 3 pathways versus 1 pathway. Splitting between the 3 pathways is going to be easier. So that tells you the total resistance of the circuit. Now you should go ahead and calculate the total current of the circuit using V equals IR. You know that V equals 9. The current's what we're looking for, and resistance is 5/8 for the whole circuit. Some quick maths tell you that's 72 over 5, which is 14.4. And that current is not actually going to go through the resistors because the current's going to get split, but it will be the current in these wires that are going to and from the battery. So if you put an ammeter there, you would have a current of 14.4. But in the resistors themselves, you have to use that voltage difference, or the voltage that's always 9 volts, and their individual resistances. So 9 volts, and you got 10 ohms. I'm just going to change this to ohms for the purpose of easy maths, this problem. In reality, you should actually mess with that, but I'm not going to because I don't want to get out a calculator. So 9 volts equals current times 10 ohms. So your current in resistor 1 equals 0.9 amps. And you do the same thing for the other resistors. Resistor number 2 has 9 volts equals the current which we're looking for times 2 ohms. So that's 4.5 amps. And then the last one, R3, is 9 volts equals I times 1 ohm equals 9 amps. Now the magic of this is that if you add up all these things, 9 plus 4.5 plus 0.9, you get 14.4, which is that total current that we had there. So you can see the current gets split out between all 3 of those branches evenly, which is consistent with the conservation of current. Spooky, right? One of my fave things about circuits. Now, things do get more difficult than this. You've probably already seen series and parallel circuits in pre-AP physics, or if you skipped that, you may not have seen them. But those are fairly basic circuit things. In this class, we are going to work a lot more complex circuits. Some of them are going to be combinations of both series and parallel, and eventually we'll add in capacitors as well. So things are going to get more complex. This is a series of steps on how I personally solve circuit problems, and I think it's a fairly good method, and it's straightforward and it's easy to understand. But if you have other ways of solving circuits, those are fine as well. I mean, as long as they get you the same answers, that means they're also valid. I'm not going to read through this slide. It'll be here in the slides for you to refer back to. I'm just going to work a problem and show you how I do it. This is an example of a circuit, of a complex circuit. It does only have 1 battery. We will get into some that have more than 1 battery. Those are super fun. But it's got all of these resistors. Some of them are going to be in series. Some of them are going to be in parallel. And we're going to look at how all of it works. So one thing that I like to do that we haven't done yet, that's kind of weird, is I like to draw my circuits, redraw them from the diagram in kind of a straight line instead of in this thing. Because here, for me, maybe it's different for you, but for me, it's hard to tell what's in series and what's in parallel, and to get it all correct. And that's because you've got these things that are in series with the things that are in parallel. So it's hard to tell. So what I like to do is draw it straight line. And it's really good to do and to keep as neat as possible, because a lot of the circuit work is just going to be bookkeeping, especially on these more complex circuits. So the way I draw it in a straight line is by starting out, let's see if I can get all of my tools correct. I like to start out with a dot for the positive terminal of the battery, and I'm going to put the voltage on that. This is positive 10. And then I start at that positive terminal on the battery and think my way through the circuit. So starting here, moving through, and I come across a 5 ohm resistor. So I'm going to draw that in the circuit. Got some wire, got a resistor. It is 5 ohms on that resistor. And that's all I do. And then we keep going. We get to a junction. Whenever I see a junction, I take my line diagram and I split it. Okay? That's a junction. I'm going to have 2 different paths, path 1 and path 2. On my top path here, I'm going to do this one. Doesn't matter which goes top or bottom. That one that has a 10 ohm resistor right there. So on my top thing here, I'm going to draw a 10 ohm resistor. And on the bottom one, I'm going to start drawing the other path. So the other path comes across a 2.5 ohm resistor right here. So that is 2.5 ohms. Cool beans. Keep moving on. On the 2.5 ohm path, I come to another junction, which means I have to do another split in my line diagram. One side, I'll make it the top side, is going to go down through this 15 ohm resistor. I know my little labels there are slightly off, but here we'll put a 15 ohm resistor. And on the other path, we'll have a 10 ohm resistor. Okay, and then if you continue on that path, you come across another resistor that's in series that is 5 ohms. So on this path, I have a 5 ohm resistor. And then that path connects back up with the 15 ohm path. So we'll close off that little section. And then that will connect with the 10 ohm section, closing off that path. And if you follow the rest of the way, you end up at the negative terminal of the battery where the potential is 0. So that is the whole circuit drawn out in line form, which is a little bit easier to understand and evaluate. From here, I'm going to start simplifying this until I get basically one giant resistor instead of all of these little ones. The first circuit part I'm going to simplify is this one down here, the smallest parallel circuit, which has these 3 resistors. To evaluate this, you can add up the 10 ohm resistor and the 5 ohm resistor. You get 15 ohms there because you add resistors in series. And then we're going to take that and add it in parallel to the 15 ohm using reciprocals. So you do 1 over 15 plus 1 over 15 equals 2 over 15. And if you take the reciprocal of that, you get 15 over 2, which is 7.5 ohms. So basically, instead of that blue sub-circuit, you can just put a resistor that has a resistance of 7.5 ohms. And I know it's a lot of work, but I'm going to draw out the line circuit again, but with the 7.5 ohms instead of the sub-circuit. So we got a 5 ohm resistor to start off with, branches off into 2 parallel lines. One has a 10 ohm resistor. The other one has a 2.5 ohm resistor with that 7.5 ohm resistor that we just calculated. And those connect together, head off to the 0 voltage negative terminal of the battery. I'm going to highlight that little 7.5 ohm resistor in blue to remind us where it came from in the previous diagram. Now we can simplify this larger circuit, the larger parallel one, which I'm going to highlight as green, and take that and make it one resistor just like we did with the previous circuit. We start off with the same 5 ohm resistor we've had the whole time, and we're going to simplify this green circuit. You do that by adding the 2.5 and 7.5 ohm resistors to get 10 ohms because they're in series. And then you've got two 10 ohm resistors in parallel. To add those up, you do 1 over 10 plus 1 over 10 equals 2 over 10, which is 1 over 5. You take the reciprocal of that, you get 5 ohms as your total resistance for that green circuit. So instead of that whole sub-circuit, I'm just going to put another resistor on the line diagram that's 5 ohms. Highlight it in green to remind us where it came from. And then you just have two 5 ohm resistors that are in series, which is super easy to add up. It's just one big resistor that is 10 ohms. So the equivalent resistance of this whole circuit is 10 ohms, and we can use that to calculate the current. According to Ohm's law, V equals IR. The voltage of this circuit is 10 volts. Current's what we're looking for, and the equivalent resistance is 10 ohms. So the total current of this circuit is 1 amp. Minor explosion in the background. From here, we can start calculating all of the various currents and voltages across all of the resistors in the circuit. This is a very lengthy process, kind of tedious, but this is where good bookkeeping skills become important. So we know the voltage and current in this last line circuit because it's just the total for the whole circuit. But if we go up to the previous circuit, this one right here, we can calculate the voltage drops across each of these two resistors because we know the current is the same in series. So for this first section, I'm going to start writing in blue so we don't get too clogged up. All right, so this first resistor here has a current of 1 amp because we calculated that. So according to Ohm's law, V equals IR. The voltage across will be the current, 1 amp, times resistance. So voltage equals 5 times 1, which equals 5. Current, we know, equals 1. So on this first resistor, that one's all done. V equals 5, I equals 1. That resistor stays the same the whole time. This second one has the same, because it's the same amount of resistance. You get current is 1, and the voltage equals 5 because it's 1 times 5. So we know the voltage across that whole giant green sub-circuit. Now as you move up to the next one, you know from here to here, the voltage is 5. Sorry, I wrote that wrong before. The voltage is 5. Now across this resistor, you have 5 volts. 5 equals I times 10 tells you the current here equals 5 divided by 10, or 1/2. And we know the voltage drop across there is 5. Now on this other side, we again know that the voltage across is 5, and the current is going to be 5 divided by 10, which is 1/2. So the current through each of these resistors equals 1/2. But the voltage drops will be different because they are in series. So to find the voltage, you have to do that current times the resistance. 1/2 times 2.5 is 1.25. And 1/2 times 7.5 is 3.75. So you have now found the voltage and the current of each of those resistors on that circuit. Now you got to take the voltage and resistance from this resistor right here, which is equal to this sub-circuit, and calculate out voltage and current through each of those resistors. I'm not going to do that just to save on the length of this video, and because it's the same process as the previous sub-circuit that I calculated, you can work the rest of that one out on your own. This is a pretty complex circuit. It has a lot of components. However, things are going to get more complex because we're going to start adding in multiple batteries and using Kirchhoff's laws for loops and junctions, but we won't get into that until next class. For today, just go complete some of your homework from Chapter 9 in the Pearson textbook. If you haven't gotten into the Pearson textbook online, you need to do that because that's where all of our homework assignments will be housed from now on. If you're having technical difficulties, let me know. All of the instructions are located in the top of your Google Classroom.